welcome back. In the last lecture, what we did was to look at the relation between the pressure difference across a membrane for non-electrolyte systems. Today, we are going to look into electrolyte systems, which was first described in detail by Dunan, and sometimes called Dunan equilibrium as well. Okay, so the concepts are similar, but let me first go into details so that you can appreciate all these expressions which we are going to make use of it. So remember, it's not important to remember the expression in the final state. For the case of a Van-'t-Hoff equation, which was derived for non-electrolyte, phi is equal to CRT, something which we can remember. Why? Because this is analogous to ideal gas equation of state. But what we are going to talk about for the electrolyte will be a little more complicated. So let us consider a chamber like this, separated or divided into two parts by membrane. That this membrane exhibits ion selectivity. Okay, and this the reason is that many natural systems, such as for example a body, have such kind of membrane which permits certain types of ions and rejects other ions. Okay, so I am going to make use of the same concept here. I will say this is alpha phase and this is beta phase. Okay, now this is at before equilibrium. Let us say you had or the system had N plus, okay, and R minus, okay, and R is much larger than Cl minus. So, and in this case you have Na plus and Cl minus, okay, and the water is there. So, water is in excess, and all these concentrations of these ions are very small. So, ionic concentration are small. Okay. So, this is basically a system which we are looking at it. So, let me also write this, that R minus anion is larger than Cl minus. Okay. So, what happens at equilibrium? So, since the membrane will allow Na plus and Cl minus and will not allow the R minus to come to the other side. So, certain amount, let us assume that, gets depleted from the beta phase and goes to the alpha phase. So, what happens here, that after equilibrium you have a situation something like this. Okay. So, this is again alpha, beta, and now I have to also mention some kind of concentration. So, initially let us say this was C 0 alpha Na plus for the case of Na plus, and this is C 0 alpha for the case of R minus, alright, and this is again C 0 beta Na plus, C 0 beta Cl minus, alright. Now, in this case now you have Na plus, R minus and as well as Cl minus. Okay, here you have of course only Na plus and Cl minus. Okay, so what we are going to do is we are going to just define C alpha as the final state, Na plus, similarly C alpha R minus, and C alpha Cl minus, and similarly here C beta N plus, C beta Cl minus. Okay, now system is electroneutral. Okay, so neutral. So, essentially in the final and in the later state both would be the same. So, electroneutrality requires that that in this case if you look at it, that means the concentration of Na plus C 0 alpha should be same as C 0 alpha R minus, alright, that must be maintained, that is initial condition, and as well as C 0 beta Na plus should be same as C 0 beta Cl minus. Okay, so that is a condition which we should have, right. Now, after change, we assume that some amount delta is the change in the amount of concentration in, let us say, sodium, okay, in alpha phase. Okay. So, that means some amount of sodium, which we are going to say delta, moves from the beta to alpha phase. So, let me write here. So, let delta is the change in sodium plus concentration in alpha after equilibrium. Okay. Now, note that R minus cannot move from the left hand side to the right hand side, remember. So, now sigma is changed, which in the beta phase also you will have some changes in the sodium of the same amount and as well as the chlorine of the same amount. Okay. So, because at the end you need to maintain the electroneutrality. So, at equilibrium the kind of concentration which we will have is as follows. For alpha, C n plus alpha is C0 alpha Na plus delta. Okay. Similarly, that it is also going to be delta. And for the case of R, it will remain as it is. Okay, there is no change in that. For the case of beta phase, you will have C beta Na plus, this is going to be C beta minus delta, C beta Cl minus is equal to C0 beta Cl minus minus this, okay. And of course, there is no there is no R, that means we can simply say this is going to be 0, okay. So, this is the condition which we have. Now, the question is how do we evaluate delta, okay. So, to evaluate delta, we make use of the condition of equilibrium and we will start only with the chemical equilibrium. So, we will just look at the chemical potential equality. So, to evaluate delta, what we can do is we can consider first, we will just consider the solvent, okay. So, consider for solvent mu s alpha is equal to mu s beta, okay. So, what we can do is, this is just for the solvent, remember, okay. Now, what we need to do is we need to connect to the pressure, okay. So, that is what we have also done when we looked into the osmotic pressure. So, we will make use of those expressions. So, let me just write down this as mu s alpha as a basic definition and connecting with the activity as mu s pure at certain temperature and pressure plus R T ln S S alpha, okay. Now, this I can also use this del mu by del P molar volume at a constant temperature and consider from P is equal to very small value 0 to certain P, and if I do that I can write this as this plus P alpha, considering this to be incompressible. So, if you integrate this, right, you are going to get from very small values of mu for the pure. So, this is at T is equal to Tp, right. So, you will get it like T and P goes to 0, okay. It is like this. If you can't get this, this is like mu S pure Tp is mu S pure, or minus if you say pure T, okay, assuming to be P equal to 0 plus V S pressure is P minus P0, okay. That is the idea behind it. So, we plug in here and then this is going to be RT ln AS alpha. Similarly, this we can do for beta phase. Okay, and then this would be considering a solvent, same conditions. So, if you subtract this, it is going to be basically 0. So, you plug in this expression here, this you can plug in here, okay, and if you do that, we are going to get the following: RT ln AS alpha divided by AS beta, and this should be P alpha minus P beta times Vs, or I can write it as RT by Vs ln AS alpha by AS beta. This is pi. So, I got a osmotic pressure expression, right. This is the standard osmotic pressure expression based on simple analysis. The key is now to connect to this other ions, the concentration of the ions. How do we do that? So, let me also elaborate a bit. So, note that just like a solvent, chemical potential should be same. Similarly, the salt chemical potential in the two phases should be same. Okay. So, that means mu NaCl is equal to mu NaCl. Now, though this dissociates, okay, so you may tempt to just say that mu of Na plus in alpha should be same as mu of Na plus in beta, but this is something which you cannot do that because you have a salt which is at equilibrium, not individual ions there. Okay, so that most of the easy mistakes which we do, but you can, if they dissociate, you can separate it out. Okay, then considering this that you are, or this ion get totally dissociated, you can write like this: for alpha, this should be same as for beta. That you can write, not for individual one. Okay. Now, what we can do is we have this expression. This is an ion selectivity membrane. This is because if you consider then the see the thing is now this is a problem if we write it. So, we have, this will be unequal because even if it is a ion selective membrane, because of the fact that the electrical potential in alpha is not equal to that in beta. So, since the electrical potentials are not same, which essentially means also that there is a concentration gradient also. So, which basically means that we have chemical potential will not be same, particularly for the ions. Okay. So, this is subtle. We can look at the final expression and you can realize that. Okay, because so what is being done here is that it's not like a free flowing condition. So, you are letting not one of the ions not to move. Okay, but then you have electrical neutrality in other say another place, but that means that there is a changes in that. Okay, and so it's like a physical barrier, which is enormously. Okay, so let me make use of this expression which I wrote it here. Okay, so this expression, the way we have expressed the chemical potential for solvent in terms of activity, we can also do that for the same, for sodium ion, for chlorine ion and so forth, right. If we do that, and let us assume that you have get rid of all these things which we have written in terms of star, right, and you can simplify, then you can show that in terms of this ion, pi will be RT. So, without going into derivation, divided by the, instead of molar volume of the solvent, because we are talking about the ion, it will be partial molar of Na plus partial molar volume of Cl minus, and then the log part. So, log this is a ratio of alpha, a ratio of activity in alpha and beta phase. So, in this case it will be AN plus beta ACl minus beta divided by, because log A plus log B will be log A times B, multiple of A's, and here is going to be A alpha Na plus A alpha Cl minus. So, this is something which you can understand, because it is the same derivation, right. So, if you look at it the way we have done it in the same way. So, instead of this will be replaced by the ions, but there are two ions. So, you will be looking at log RT ln AS A N plus plus the Cl. So, this is same as if you had used the solvent, right. Okay. So, now we have a common expression which relates this. Okay. So, for the case of a dilute solution, now when you have a dilute solution, the activity of the solvent would be 1. So, you have AS beta is equal to AS alpha is equal to 1, okay. And in that case, for solute we can simply write concentration, okay. For AI of the solute can simply be written as a concentration. I can actually show that in a later part when we are going to derive a bit more. So, this is for solute, okay. Then what we can do is we can again go back here this expression, okay, and so this, if we use these two expression, okay, because remember that what is our purpose? Our purpose is to get delta, all right. So, now this is going to be 1, okay. I can write this as A Na plus beta ACl minus beta divided by Na plus ACl minus alpha alpha. So, this RT gets cancelled, this part goes here, this can go to the other part. So, this is nothing but AS beta, that is superscript, the rest of the term will be here. Divided by Vs. This is what it is. So, this is 1. So, that means, well, the rest is 1. So, that means this is equal to this, right. So, this is equal to this, but since we have said that A is nothing but a concentration for the solute because of very dilute solution, then I can write this as Ca as right. Okay, so now we have come to this expression, okay, and from here I should be able to evaluate the delta. The delta, that is the amount of the concentration which changed from beta phase to alpha phase. How I can do that? By just replacing this expression to the expression which we have written, because initially remember that we know the concentration. So, Cna plus lambda was simply this, and this was nothing but delta, and this will be your C0 Na plus beta minus delta to the power square, okay, because this will be also the same, because both were same initially. So, this becomes delta is nothing but so this is the final expression which we can derive. So, I will not go through the details, and the key is basically not this expression to remember. The key is the way we have derived, okay, and what are the assumptions we have taken. You can also write this expression in terms of the fractional amount of the change with respect to the original concentration level of Na plus, okay, and I can obtain this kind of value. Yeah. So this was the amount, the delta. What about pi? Can we come up with the expression which is much more convenient? Now remember that pi for osmometry, which we have looked into for non-electrolyte, we said pi is just proportional to the concentration of the solute. Okay, so pi is equal to C2R2. So in the same way we can actually obtain here also. Here also there will be the concentration difference between the two segments or parts of the membrane, but let me write down the final expression, but I will show you, I will derive as well. So this will turn out to be something like this: C0 alpha plus minus C0 beta Cl minus plus 2 lambda. So this is the expression of the osmotic pressure which relates to the concentration, initial concentrations, okay, minus of that plus the changes also, okay. So but in principle one can show that osmotic pressure is simply the difference in the solute concentration between two sides. So how do you prove these aspects? So and here you will realize some of the approximation which we have taken plays such a significant role in getting such expression. So let us go back to the expression of pi in terms of the solute or in terms of the solvent. Right, this is something which we have derived, and this derivation we remember, you know, if you can, it is easy to remember, otherwise you can still derive from the basic expression. Now since this is a dilute solution, gamma solvent is going to be 1, correct, that because it is very dilute solution. So I can write this simply as correct. Now what is x of s? This is going to be 1 minus, so we are talking about beta, so beta phase, okay, alpha beta, remember the alpha is on the right hand side, left hand side, and beta is on the left hand side. So beta is this, so Na and Cl minus only, and alpha will have R also, right. So I will write here minus x Na plus beta. What about alpha? 1 minus x Cl alpha minus x Na plus alpha minus x minus alpha. So this is the two value, okay. Now since it is a dilute solution, so considering solution, log of 1 minus A is minus A, okay, is approximate we can do, okay. So this x are very small, that means if A is very small I can write it in this way. So now I can use this approximation for this ln of xs and ln of xs alpha. So if I do that, the following I can write, that pi is equal to RT Vs. So the numerator is beta, but finally I am getting minus of A, okay, and remember alpha is in the denominator, I am going to get positive value. So I am going to write it alpha first, alpha plus x Na plus alpha plus x r minus alpha, okay, minus x Cl beta plus x, okay, I have this expression. Now what is xi? Typical xi would be, I mean the basic definition of xi is Ci divided summation of Ci. Now considering that since the concentration of the solutes are negligible, so I can write this as Cs, concentration of the solvent, and we will assume that Cs multiplied by Vs is nothing but 1, right. I am going to write Vs as 1 by Cs, right, So, now I can replace this X in terms of C. Okay, so this is what I am going to get, this as RT CCl plus CNA plus alpha plus Cr minus alpha minus CCl minus beta plus CNA plus beta. Okay. So, what is this? This is delta. What is this? This is C0Na plus lambda plus delta, and this will remain as it is, C0 R lambda. Okay, and this is C0 beta Cl minus lambda. This is again C0 beta Cl minus lambda. Okay. So, I now can summarize this. So, if you reorder this, okay. So, for example, I have written directly this as this because C0 Na minus beta is nothing but C0 Cl minus beta. Okay. So, with this I can get an expression of 2 Na Cna 0 alpha plus 2 this minus 2 Cl minus beta minus 2 lambda, and this is nothing but 2 RT okay. So, this is the expression which we said that, okay. A very systematic, but the key is the dilute solution, okay. You have to make use of the approximation very well. Okay, so the last thing which I am going to make a comment is that since there is a difference in the concentration of the sodium between these two parts of the chamber, there will be a electrical potential which will be developed. Okay. So, this electrical potential effect is phi, this will be RT Na, Avogadro number is what? Charge electron, and this is the coordination number or the valence number of sodium, which is nothing but only 1, all right, log of A beta Na plus A alpha Na plus this is nothing but Nernst equation. Okay. So, this is the electrical difference in electrical potential, okay. And this is the beauty of such a membrane, because based on that you can find out effectively what is a concentration which is available. So, in other words, I can relate this expression to the concentration also. Without deriving, I am going to write it here. Okay. And this electrical potential can be measured experimentally, and you can understand the membrane property very well. And this particular aspect is extremely important in biological system because of the fact that many biological systems are ion selective. It is also very relevant in industrial separation if it is a charge membrane. Okay. And thus this understanding is quite important for practical applications. Okay, so with this I am going to stop, and the next lecture I will take up an example, and in addition another topic particularly the solubility of solids in compressed gases. Okay.